A very interesting day. So it's my pleasure to introduce to you this morning's keynotes, and starting with Stephen Wolf. Stephen has worked in the NREN community for around 30 years. He's also worked at the US Army Ballistic Research Laboratory and in the Army Research Offices, as well as the US National Science Foundation. He's worked at Cisco Systems and at Internet 2, where he's currently the VP and CTO. He's a member of the ACM, IEEE, and ISOC, from whom we received the Postel Award in 2002. So a distinguished speaker to get us going this morning. Stephen, please.
Thank you, David. Thank you, David, and thank you very much. And it's a great pleasure and an honor to be here this morning and to speak with you. The title of my talk is intended to say that I'm focusing on the future of NRENs, and so I have to apologize to all of those whose NRENs may already be in their third iteration, but we're not. A little later today, in the next session, my CEO and colleague, Dave Lambert, will talk to you about the social and economic changes that are likely to be facing NRENs in the near future. I would like to talk instead about some technical things. And as I was preparing for this talk, I came across this article, a report from a market research organization, McKinsey, 12 disruptive technologies. And there are 4 or 5, I think, interesting and important notes to make about this set of 12 things, 12 activities, 12 technologies. The first, of course, is the one that at the bottom of the screen there that says that they forecasted in 2025, that's a dozen years from now, that these technologies will be responsible for about 33 trillion US dollars of the global economy. That's what, 33 times 10 to the 12th. That's a lot of money. Especially given that the total economy at that time was forecast to be about 100 trillion. So these 12 technologies alone are going to account for a really substantial fraction of the global economy. There's some things to notice about these when you look at them and you think about our universities, the ones whom we support. You see that each and every one of those technologies is currently under active research and or development in our university community. I spent 20 minutes with Google and found quite a large number of university projects, right? University research projects, having to do with these 12 technologies. Another thing to notice about these is that in the stage that they are in today, where they're being researched in universities, the network is an essential part of that research, because each and every one of these that I looked at had at least one large group research project. And the group clearly is connecting itself through the network, through our networks. And even when these technologies are reduced to practice, many of them, though not all, will rely on the network for their operation. You obviously cannot have a semi-autonomous vehicle without a very large sensor network that is communicating with that vehicle all the time about road conditions, about the activities of other cars on the road near it, weather, and all that sort of thing. So the network is an essential part of each of these technologies. And finally, if you look at those technologies and you ask yourself, what's missing? What's missing? What's missing from that list is our old friend, big data. But big data is the primary driver of all of these things. All of these technologies in their research phase and often in their practical stage, in their useful stage, rely on vast amounts of data. Now, we're all familiar with these classical examples of big data, right? The major genome sequencing centers at 2 petabytes a year, the Large Synoptic Survey Telescope at about 10 petabytes a year, LHC at 30 or more when it cranks up again. The SKA, raw data, an exabyte per day. I'm not sure what the process data is, but it's still a very large amount. But there's more to big data. There's the long tail. There's the long tail of the rise of team science, particularly in disciplines where we have not seen it before, and in some sense, we're surprised to see it now. There's a report from the National Science Foundation. To a very considerable extent, statistics and applied mathematics and parts of pure mathematics have become a group science. Now, if any discipline has a stereotypical lone investigator, it's pure mathematics. And it's rather startling to see pure mathematics tagged as a group science. There's a recent report from a library organization, CLIR, talking about computationally intensive research in the humanities and social science. A few months ago, we at Internet 2, in collaboration with Microsoft, ran a workshop on social science, cyber infrastructure for the social sciences. And of all organizations, the Institute of Electrical and Electronic Engineers this October is hosting a workshop on big data for the humanities. That's a culture shock, at least for me, if ever there was one. And of course, the teams in this team science, both in the very large projects as well as in the long tail, the teams are not local. We are all accustomed to thinking of research being global, but that's being brought home in spades. The LHC, 36 countries participating. At Internet 2, we did a survey of joint collaborative projects between the US and India and between the US and China. And we found that with India alone, we have over $2 billion of joint research projects funded by the two governments. And many of those, more than 360, valued at $250,000 or more. And despite the ambivalent relations between the Chinese government and the US government, research is doing very well, thank you very much. Had over $1 billion of joint research projects, and many of them quite sizable. So research is truly global and becoming more so. Of course, higher education is undergoing the same transformation. New York University, I believe, has 11 remote campuses in other countries. And this is not a US phenomenon. Many other countries have universities who are going global. We have, of course, classical distance education, which has always been around since the web. And the newly emergent technology of the MOOCs, the massive open online courses, where a particular course may have 1 million or more registered students. They are perhaps an unexpected and new version of big data. Well, we've all heard that data are growing, right? The accumulation of data is growing faster than Moore's law. So it's reasonable to ask ourselves, how are we doing in the networking business compared to that? well, I can only speak with some authority on one NREN, and that's the one in the US. We started around 1985 at 56 kilobits, and so it marched up the ladder, as you can see, from T1 to T3, to OC3, to OC12, to OC48, to 10 gigabits, and finally this year to 100 gigabits. And we were sort of staying comfortably ahead of Moore's law, but not by much. There was a 9-year period there at 10 gig, which oddly enough coincided with a period on campuses where the campus network became consolidated, it became very competent, very professional, extended throughout the campus. It became incorporated into the campus IT organization and became, I'm afraid to say, quite risk averse. As I think we will demonstrate with our move to 100 gig in the national network, we hope to change all that. Not because it's something that we want to do, but because the rise of globalization, of big data, these characteristics of modern research and education are forcing campuses to change. So what we might think of to try to keep up with the rise of data is new technologies for the network itself. We've pretty much exhausted taking the innovations in wireless networks and moving them up to optical frequencies. The only really new thing that seems to be coming down the pike is taking advantage of the observation that wavefronts of light don't necessarily have to be planar. They can, in fact, be helical. And if you have a helical wavefront, you can conceive of interleaving another helix with the first one. And then you get two, hopefully, non-interfering channels on one beam of light. So this is being pretty widely researched in photonics laboratories around the world. One that I know about is Alan Woolner at the University of Southern California. He has demonstrated 42 wavelengths, and on each wavelength he has 24 helices. That's 15 degrees separation. Right? This gives him something like 1,000 channels, and he's running 100 gigabits on each channel. And this puts 100 terabits, which is pretty spectacular. Now, mind you, this won't work in the atmosphere because normal atmospheric turbulence sort of mixes everything up. And he's only demonstrated this in a vacuum over a distance of about 1 meter, I believe. But that's all right. That's a beginning. That's a beginning. The spectral efficiency of this is about 100 bits per second per hertz, which is pretty spectacular. But of course, you can't beat Shannon's law. If you're going to get that kind of signaling rate, you're going to have a pretty spectacular signal-to-noise ratio to achieve it. So, as this gets reduced to practice, if it can be made to work in fiber, we'll be able to substantially increase the bandwidth of our networks. Well, I guess so. 100 terabits, right, on one beam of light. The Internet 2 backbone in the US today has 88 channels of 100 gigabits. That's 8.8 terabits. So even this radical technology is only going to give us about an extra order of magnitude. That's not really going to stay ahead of Moore's law for very long. So I think we have to cope with and respect the fact that our networks are never going to be able to catch up or keep up with the growth in the amount of data and the amount of data that people want to transmit and convey from one place to another. We're just not going to be able to do it. Now, on the other hand, Big data is not all bad. Big data has, after all, led us to some fundamental advances in the understanding and design of networks. Starting back in 1988, when Van Jacobson was trying to FTP the Berkeley Unix source code up from the university, which he could see from his window. Right? He could see down the hill, he could see the Berkeley campus, but he couldn't get the bits up the hill. And this led to the first control theoretic understanding of the way TCP works. Fast forward 15 years to Matt Mathis at the Pittsburgh Supercomputer Center, who had exactly the same problem. His job was to move all the data at Pittsburgh to the San Diego Supercomputer Center, and he couldn't do it. He had what was, for the time, a pretty high bandwidth connection. And this led him to discover the importance of the implementation of the protocol stack in the end systems, and led to the Web 100 project, which lives today as Web 10G for the same reasons. And finally today, a innovation in campus network architectures called the Science DMZ, which most of you know about, due to our friends at ESNet. This is a scheme for keeping the elephants and the mice separated on campus so that each can get its work done without interfering with the other. What's more, big data has led to fundamental advances in science and in analytics. I have two cases here. The first I call traditional science with big data. Traditional science is you formulate a hypothesis and you gather data and you analyze it until you can either accept or reject the hypothesis with whatever statistical confidence is characteristic of your particular field. The poster child for this, of course, is the LHC, where the event, which I think they call the observation of the Higgs-like particle, at the output of the detectors at the collider, the signal-to-noise ratio was something of the order of 10 to the minus ninth. They collected enough data so that at the end they were able to announce that if what they saw was a random event, it was a 5 sigma event, which is, I think, something like a part in 2.5 million. The second form of big data in science is the scheme of things outlined in the little monograph, little essays, collection of essays called The Fourth Paradigm, in which the data themselves are allowed to suggest a hypothesis, which you then can verify by taking even more data and trying to verify or reject the hypothesis. But this is leading to whole new areas of understanding in analytics, in learning algorithms. How do you cope with data that are coming so fast you can't possibly analyze it all, and you have to figure out how to analyze pieces of the data, unstructured data, visualization, dimensionality reduction. All these are active and new fields of mathematical research and statistical research. So this collection of trends in big data and in the network technology, leads to some implications and some consequences. In the first, with apologies to John Donne, no NREN is an island. Your faculty, your researchers will not permit you to be an island. You have to be part of the whole. Team science. What we are discovering is that virtual organizations like to have their own network. Right? The LHC project, for example, ended up with its own network to do the analysis. Its own network to which outsiders were not allowed. Now, own network means various things. It can mean everything from owning your own fiber to having your own VLAN and everything in between. And as we just found out, big data means more than just big pipes, because big pipes are not going to handle everything that big data can throw at us. Now, to elaborate these implications a little bit more, globalization. It's the patchwork of intercontinental connections which has served us well in the past, is simply not going to scale in the new generation of things. We can't afford to upgrade all those links, or to contemplate even having that many links at 100 gig between continents. It's time to think about an engineered global research network, a GREN. This is not an organizational suggestion by any means, but it is an intellectual imperative. We have got to think not of our own NREN. We should not think of a collection of NRENs. We have to start acting and believing and procuring like a global enterprise, because that's what we are. And only thinking in that way will enable us to move forward. Team science. The one-size-fits-all IP network, which served us well for many years, is not going to work in the current climate, and the climate as it's developing. Software-defined networking, OpenFlow, OSCARs, and whatever comes after those, will help users, and much more importantly, applications, configure the network for the particular case at hand, the particular job at hand. And this will allow virtual organizations to configure networks for the task at hand on a dynamic timescale, rather than taking minutes or days or weeks as it can today. And finally, re-architecting the campus network. This will become increasingly important as the number of large data projects on campus increases. It's going to be absolutely necessary to understand how to get large data flows into and out of campuses. So there's the Science DMZ to re-architect the campus network. There's tuning event systems with Web10G. And finally, to figure out just exactly how the network is working, measuring its performance. We like perf sonar because we invented it, but it seems to be a pretty popular and useful measuring tool in use around the world, and we look for its increase. Well, after thinking about these things for a while, a light bulb lit up in my head. And what we call data, folk in other lines of endeavor call content, one of the much overworked words. But if data is content, if we're talking about moving data around, if data is going to be the governing principle of our networks, perhaps a network node needs to look something like the picture, in which there is a large data store and a large router. Well, let's not call it a router, let's call it a switch, right? And the function of this switch is not only to connect to other nodes on the network, but it functions, at least in part, as the top-of-rack switch for the data store. So at the configuration of the data store is under control, can be under control of the network, and vice versa. This is quite an old picture. This is a picture from 2009. It's due to Professor Doug Comer from Purdue. Doug's one of those guys whose radar sees a little bit farther over the horizon than most other people's. So that's why the picture's a bit dated, but I think there's something to it. Well, this brings us, however, to the black swan. That is the conclusion that we should have seen was coming. There are a growing number of instances in which the data are just too numerous to move. The rule of thumb, of course, is a petabyte is 100 gigabits per second for a day. If you have several petabytes of data to analyze, unless you have lots of time on your hands, you're going to spend a lot of time moving data from where it's stored to where you are. In almost all instances, it's going to be easier and faster to move the computation to the data in one way or another. You can even, if you have compatible architectures, you can just move a binary over the network to where the data are. So this is cloud computing, for which the currently popular programming model is MapReduce, Hadoop being the open source version. You know, that's fine, but it's not well suited to, not well adapted to most HPC architectures. Most HPC machines don't have a disk at every node. Of course, if you had a programmable switch, you know, you could take care of that, couldn't you? I mean, you could configure your collection of servers to do Hadoop, and 10 minutes later you could, if you wished, configure the blades into I don't know, 5D toroid, you know, which is one of the ever popular HPC architectures. Well, that's just speculation, I suppose. If you follow this line of thought further, you get to the point where not only can you not move the data you want to analyze are distributed around the world. There's, you know, a few petabytes here, a couple of petabytes there, and you're somewhere else. And so, yes, there's a figure that I read. If you really want to have all your data in one place, if you have 10 exabytes of data on disk, it'll take about 2.4 gigawatts of electrical power, and that's pretty hard to come by. So large data sets are not all going to be in the same place. Computation in place then means the global R&D network is the backplane of your computer. Well, it's a high latency backplane, but you have to take account for that. So this leads me to the notion of convergence. Computers, data stores, and networks are all now programmable. They're all being brought into the general understanding of computer science. Networks are not something special. They're just a piece of computer science. Databases can be treated as a regular part of computer science. There's a convergence. The computation models, multi-computer architectures, network architectures, storage architectures, these are converging disciplines. And what this means is that as network engineers, we are all going to have to learn some new skills. You know, being conversant with the CLI of your favorite router vendor is just not going to be enough anymore. In addition, because of the new flexibility and complexity of the overall computational environment, we need support staff who are not only conversant with the network and conversant with the computer and conversant with the storage facility, but they are experts, or at least journeymen, in computational X, fluid mechanics, structural mechanics, particle and cell, free boundary problems, you name it. We need support staff who are disciplinary experts, as well as being able to program everything. This is a fundamental change that we're going to have to cope with. This is a social change in our networking society. I have only one boot note. Right, this is something that's not exactly related to the talk. the bringing of new communities into the computational spectrum, communities that don't have a history of large-scale computation, are giving us a new set of problems. There's this quote from Miron Livni: "We're faced with a group of scientists who are analyzing data they did not collect, using software they did not write, on machines they do not own." This is, the pejorative term for this in the hacking game, these are script kiddies, right? We don't want that. So we need Renaissance thinkers in the support staff. We must begin also to think about peer reviewing scientific software. There's this article in Science magazine referred to at the bottom of the slide, in which scientists in a particularly new field of computational science were asked why they chose the piece of software that they were using, why they chose the software package they were using. Well, they chose it because one of their colleagues recommended it. They chose it because they'd seen a lot of papers written using it, but none of them said they had analyzed the software and it was doing what it claimed it to do. So this is another complication in the computational scene. That is the primacy of software and its provenance. That's all I have. Thank you very much for listening.
Thanks, Steve.
Yep.
So I think we've got time for a few questions, if anybody's got something they would like to ask. Anybody? Ah, yes, there's one here.
Hello, Steve. Good morning.
Morning.
It's Michael here from RMP Brazil.
Yeah.
Have you thought of addressing the question of where do these polymaths who are going to be computational scientists with all these skills will be trained, nurtured, put on the job? And this seems to be the next step, which is essential.
It certainly does. And there are universities, at least in the US, who are trying to train people like this. Clemson is one of them, and there are others as well. Trying to build a cadre of practitioner support people that are polymaths, as you call them. There is a project in the US, which we all hope will get funded by the NSF, called the Condo of Condos, one of whose principal activities will be to develop exactly this cadre of practitioner support people. So yes, we have given some thought to it.
Do we have another question? Yep. Inda.
Steve, an excellent talk. I really enjoyed it. So I have a question about infrastructure. Now you talk about global research and education network, and we only think of, routers, switches, bandwidth. But one of the key infrastructure, like you pointed out almost near the end, is actually going to be software, because it's now has to be treated as a part of your infrastructure. It's critical to providing service. So when you talk about that, the community doesn't have a good model for maintaining and contributing to open source software that we use. And organizations don't seem to consider that as part of what is needed to build and maintain their infrastructure. They don't put money aside to invest in it. So how do you think that realization can come about in the R&E networks, and how can that be supported better?
Thank you, Andrew. That's a really tough question, and it's one that we're grappling with all the time. It's the tragedy of the commons, in a version of the tragedy of the commons. Open source software is everybody uses it, nobody feels responsible for it. In many places, it's a labor of love, as Oscars and Personor has been at ESNet. It varies from NREN to NREN. Some NRENs have support staff for precisely this purpose, others do not. I think it's a global problem, and it's one that should be addressed. In addition, the open source software is easy. We don't have a good way to peer review or even to think about proprietary software. And there are a number of proprietary software packages that are becoming more and more popular as big data becomes more and more important. And we don't have a clue how to handle that. Yeah, you've touched a very raw nerve, absolutely.
Yeah, one more. Two more, in fact.
Okay. Hello. Okay, Daniel Kahnberg, RIPE NCC. Hi, Steve. I liked your talk. I also liked your speculation of racktop switches morphing into something more global. But what I missed a little bit, and I agree with you, just to set the stage, that at least part of the computation will have to move to the data or with the data. What I missed a little bit beyond that speculation is what kind of a strategy would you recommend for NRENs to get to the GREN? What are you doing to actually facilitate that moving of computation?
Well, I think you alluded to two things. How do we get organized to do that? And then what do we actually do? There is, as you know, a group of NREN CEOs who are conferring about this class of problems. And I think we have to wait and see what the proposals are. But again, just to make it plain, this is not thinking of a global organization, right? It's a global network, but it's very much a federated organization. I hope that answers your question as well as I can answer it.
Okay, one last question, I think, here from Kees.
Yes, I enormously appreciated your talk, so very inspiring. I also want to point out and notice that we think of the scientific data, the e-science data, as big data, but there are much bigger fishes out there. So huge amounts of data are residing in clouds, at Google's, at Amazon's, and at other places, societal data, telecom data, mobile phone data, and so on. So how do you see, so I at least noticed that researchers are taking their research questions way more from societal and business data than from the scientific data we are used with and grown up with. So how are the NRENs going to make sure that the scientists can get to that kind of data, which is not primarily residing in the data stores of the scientific institutions?
That's another tough problem.
Sure.
As we know, getting access, for example, to traffic data from commercial ISPs is pretty much hitting your head against a brick wall most of the time. The other data, my belief is that this is a place where the public-private partnership can play a role. This is an instance where we as NRENs and as facilitators of the science have got to advertise to the owners of the data the benefits of making that data available to the scientific community, and so that they have something to gain by releasing the data. If there's nothing for them to gain, they won't do it. It's not a matter of money. It's not a matter of buying the data or renting the data. It's a matter of making them understand that our community can tell them things that they would not otherwise know. Yeah, good question.
Right. I'd like to thank Steve one more time for setting the trend of the day going now with some very interesting questions and some thought-provoking discussions to follow. So thank you, Steve.
Thank you. Thank you, David.
So now it's my pleasure to introduce Kurt Erik Lindquist. So he's the CEO of NetNod, chair of EuroIX, and in the past has served in many capacities on the Internet Architecture Board and in standards activities, working on IP engineering, IPv6, and peering for KPN Quest, amongst others, before joining NetNod in 2002. So thank you, Curtis.
Thank you. Good morning, everyone. So I have spent a large part of my history at doing peering or interconnects. And I think there's an interesting trend that I've been looking at this, and I think it's an interesting follow-up to what Steve talked about. So I'm going to start with a small history lesson. And this is mostly because in weather forecasting and in predicting the stock markets, if that's any good to go on, you know, the best bet you can say is that tomorrow will be very much like today. And I think that if we look back in history, there's actually a few things that we can learn. So we're going to do a quick deja vu through the history of the European internet. And let's see if there's something we can conclude from how this all started and what we actually did into what we think we have to do for the future. And I think it's interesting for a few things. One, because I think we're actually back in a way in where we were in the mid-90s in Europe. And secondly, because I think that there are other parts of the world who are very much where we were in the middle of the 90s. And I can probably also learn. And I think both we and them can benefit from looking at what we did then and what choices we made and why. If you look at the European internet and how peering and interconnects actually developed, you can basically divide this into three phases. The early academic days, the early commercial days, and then modern times. And in each of these stages, a few things drove development. In the early academic days, there was no competition, no real commercial interest. There was a great cooperation. This was basically the first steps of the internet in Europe and when this was built. And it was all low bandwidth, low consumption traffic. This is actually a picture that was found in one of the early, I think it's actually from a Torino publication, of the very first major interconnect in Europe, the IBR LAN at CVI in Amsterdam. And you can see it there on the bottom of this nice network topology diagram. I've been told that the thick Ethernet cable is actually still bolted to the wall. I don't know if that's true or not, but I'm sure some of you would know. But this is sort of the very first interconnects and how this started. It's very simple, and it covered sort of the internet of the days. Shortly afterwards, we had the first commercial days. That was driven by a few things. We had that I believe, the single most important thing that happened in Europe was the deregulation of the telecom markets. This allowed anyone to start their own operator or ISP if you had enough funding, or even if you didn't. You could go and provide internet services or telco services. We started seeing the first commercial demands for internet services. The first corporations started buying this. Some of the educational networks shifted the fundings to go to the NRENs, to go to universities. It also created a bit of commercial demand. And we had the first cases of players starting to form peering policies, the rules of how we interconnect and how we build interconnections in the market. And this is when we saw the first advent of the rule that both sides must benefit. And very similar development happened in the US at the same time. So it's not just Europe, but I'm focusing on Europe, and I'll come back to why. And we also started seeing actually the first commercial service offerings, and I think this is interesting, that started making PR that we have interconnects, therefore we are better than the competition. And this was the case apparently in the UK, and it was also the case in a few other countries. And by the way, I forgot to say this, but I wrote this slide deck, or I started doing this some time ago, and I interviewed some of the people who were then running some of these networks, and it was quite interesting, and because they all represented various competitors, and the history was a little bit different depending on who you asked. But that probably reflects this healthy competition. But the interesting thing is that the interconnects and the benefits that brought to the end users were seen as a commercial benefit that could be utilized, and they provide the value to the end users. And keep that in mind. We also saw the first playing. This is a Dante newsletter where Dante is threatening to de-peer EUNet because EUNet refuses to upgrade the interconnect links. The thing that Dante hadn't figured out was that EUNet was transit-free and Dante wasn't. So if they de-peered EUNet, Dante would end up paying for it and EUNet wouldn't. They later realized this. Again, we started seeing that this started having some commercial bearing, and interconnect started becoming important for how we did this. Why did people start to do these interconnects? In the mid-90s, prices were quite high. The international transit or international capacity out of Europe were dominated mostly by US big telcos that probably made a fortune on this. The European operators, in turn, the smaller competitive ISPs and competitive telcos, had to buy fairly expensive international lease line circuits from the incumbents. That again was making a fortune on this. If I could save money by not sending international traffic and keeping it local in my country, and I cooperated together with my competitors against the big common enemy, the incumbents or the US telcos, the better. We could save money and we could benefit. And people started doing this, and this was started in a few cities, and it grew all across Europe and across the continent. At this point in time, the fact that we also decreased delay and improved performance were probably less of an issue, although it did, and later that came to be more important. But we had this common enemy, and we cooperated, and we made this work. In these days, remember that the incumbents were already then against this idea, because that would cost them money, right? Keep that in mind for later. At this point in time, most of the traffic in the most of the traffic in Europe were destined for the US. All the content, all the cool websites, not to say all the websites, were in the US. Every content we wanted was a server or a server farm in the US. There were some in Europe as well, but not nearly as popular. As we grew this interconnect and as the service matured and we got more users, local content started flourishing and became much more popular. These were mostly developed to meet local need, interest, culture, language, and we see very much the same development if you look at how developing countries go onto the internet. We see the same cycle of local content being developed as local access becomes more available. In the beginning, a lot of the content is developed outside the country, maybe because of expensive bandwidth or unstable bandwidth, and as that matures, content moves closer to the end users. And this again changes the interconnect landscape because you need to have higher bandwidth interconnects to handle the increased load of local content. If we put this in a more graphical way, we went from 80%, when I started doing the internet, I'm young, so in 95, when I started doing this, 80% of the traffic went to the US. In 2001, when I did peering for KPN Quest, I made the following, that's actually why the graphic is so horrible, because that was what PowerPoint had in 2001, is that the numbers you see here, the second number is the amount of traffic in the country that stayed in the country, and the first number is the number of, the percentage of traffic that stayed on one of our fiber rings of that region. The number I think is mostly interesting is Finland. And I'm Finnish, so I can say this, but it's 68% of the traffic stayed in Finland. It never left the country. I don't know why, but I have a theory. I don't think the Finns are very good in English. I might be wrong, but it's actually interesting because you see similar numbers in other countries where English is not a very widely used language. You can also see that a large percentage of the traffic stays local. Again, this puts much higher demand on a working local infrastructure. Today, we have I just picked some very large exchange points in Europe where where you have this very high concentration of traffic, especially between Amsterdam, London, and Frankfurt. I think that's a little bit ironic, given that we built these exchange points because we wanted to localize traffic and keep it more distributed. We have now concentrated. But I think this picture is lying a little bit, because most of the content today is actually not delivered necessarily in this way. We have Akamai, Limelight, all the CDNs, together with the Google caches, have started pushing traffic out. And now we're coming to what I think is interesting. We saw this shift from traffic going all the way to the US to becoming more localized, and then more localized. And it could become more localized because we had these denser interconnects. And we started, and these interconnects started as a way to save money, but it eventually turned out that it helped customer experience, and it did so by shortening the distance between the data and the end users, just like Steve was talking about before. We also had this idea about hot potato routing. I wanted to send the traffic to the other network as quick as I could to save on my backhaul cost and force the other ones to pay, which was a good thing. It's hard to prove, but these dense interconnects in Europe probably helped innovate some of the services. But what it definitely did do was it helped to improve the end user experience. And it actually posed a threat to the business models of the transit providers, of which I was working for the most dominant transit provider in Europe. We didn't pay with anyone because we saw this revenue going out the door, right? But I no longer work for them, so I can say that I changed my mind. And I think that it's hard to underestimate this deregulation and what it actually meant. If you look at other markets where interconnects and licensing of telcos are prevalent, then it's actually, you don't have the same dynamic market. You don't have the same competition, you don't have the same price erosion for the end consumers. One thing we don't talk often about is that this has also made the European network much more resilient than in any other parts of the world. What few people know is that during September 11 in 2001, when a large part of the transatlantic capacity was taken out by power failures on Manhattan, some of the carriers, including us at the time, who actually had spare capacity, did pick up transit traffic from our competitors for free over these exchange points and brought the traffic to the US. We decided to cooperate because it was better to keep the network working than not. And these interconnects, these dense interconnects, has made the network much more resilient. I like to say that Europe today has the most resilient, most interconnected network in the world. Every time I say this, there's always someone from North America saying, no, we're much more interconnected, and I'll see you outside afterwards. No, but the difference is that the European exchanges were all, mostly as they look today, were created in this cooperative spirit where they are jointly owned by all the members. They're members-run associations. And I think that's a major difference because that has created a very good stepping stone for this dynamic market. Some that can be copied to other parts of the world, but that's not what I was going to talk about today. What is interesting is that when we had this development, again, the incumbents were the ones who lost money, and they saw this as a big threat against the revenue streams. If we fast forward to the end of last year, we had this UN conference about the governance of the internet, where a European organization called ETNO, which is the Association of European Incumbents, telcos, they proposed that we should, by regulation, force the content providers to pay the access networks. To me, that is very much the same thing as we saw happening in the past. This is just a way to get access to data. If I'm an eyeball network, I had to figure out how to pay for my own costs. It's a little bit like we would force the airlines to charge us. Right? So having these interconnects as dense as possible is quite good. It will improve the end user experiences and add this redundancy. And redundancy is quite popular right now. All the European government and European Union has these critical infrastructure programs where they want to protect the European internet. And I think this is one of the best ways you can protect this by having denser interconnects, because you can localize faults, you can isolate problems. And it also gives you a lot more control over the traffic. So there are some other benefits of this, that you get better access to root servers, DNS root servers, the CCTLDs, etc., that will again increase the resilience of the infrastructure by having more interconnects with this. We happen to run one of the root servers, and I think I used to send the peering emails to all the world's networks. We have this in 45 locations all around the world. And I made a presentation, one of the funniest responses we got back. So, I mean, a root server, you all have to have access to one for your DNS to work, and we don't charge you for running this service. But if you send this peering request to the tier 1 providers, the largest providers in the world, they will undoubtedly answer you with a price quote for transit. And we generally then just decline and say, look, it's your problem, not ours. Then they tend to figure it out. But. So, as a small example though, and this is more, what do you think you can gain from having this? Is there a financial gain? This is a provider in one of the world's poorest countries, in a small landlocked Asian country. They bought 2 SDN1s to the Links exchange point in London, and they managed to peer away 100 megabit. Woohoo! That's what I have at home. But these 100 megabits from this landlocked country actually paid for these 2 SDN1s to London. That tells you that where we were in the middle of the 90s, the rest of the world are right now. They're seeing exactly the same problems as we saw in the 90s. So, to look into the future then, what do I think we can learn from this in our environment? Is there something that we can pick up, and I think that we can, that is the history, is history repeating itself? And in my crystal ball, I think it is. And I'm going to give you an example, and well, I'm going to take a random country, Sweden. This is not because I happen to live in Sweden. It's simply because the Swedish regulator does something very interesting. They force all the operators to give them a lot of statistics of number of subscribers, market share, etc., and bandwidth, access bandwidth. And they publish this data freely. You can all go and read it. So they've just published the numbers of 2012, and the numbers aren't so interesting. They have a number of subscribers, and they have various types of access. We can see that the high bandwidth access are sort of growing, and the low bandwidth access is up here, and that's actually fairly static. But it's I mean, static in this end here. It sort of doesn't seem to decline much at the end. But the most interesting thing here is that all the large majority of access speeds are what we would call sort of high bandwidth access or broadband. Sweden has apparently 9.5 million internet subscribers, which is more subscribers than we have population, but anyway. If we assume that each of these subscribers have some sort of average utilization rate, and I told some of you that I'd never been to a Terena conference before, and I was terrified to go and talk about numbers in front of what I thought was an academic conference, because you'll question anything I say. It's an example, okay? Don't take this as science. If each of these subscribers have an average utilization rate, we'll end up at some sort of peak bandwidth of, depending on what they are. And talking to the Swedish ISPs, it seems that oops, wrong slide. There you go. That 0.5 megabit per second is sort of the average utilization. Interesting enough, no matter what the access speed is. That gives us some sort of value up here of total average volume in the network. If we extrapolate this to the market share, we know that the 5 biggest ISPs have the following amount of traffic in their network. We just split it over market share. Now, here comes the really non-science part. But I think it illustrates where I think we're going with this. According to Arbor in 2010, Google is between 8 and 12% of the network's traffic. I think it's at least twice as much, but who am I to question Arbor? It's the truth. If we assume that Arbor is right, then each of these providers at 0.5 have, 250 gigabit per second to a single peer. I think they have a lot more than that. I think it's probably several times this. But I think the interesting with this is that because we know the market share, we know the number of subscribers, And we know that the average traffic volume will go to the right, and so the utilization to this single peer, this single data source, is going to go up, and quite a bit up. Now, don't get too hung up on my example of using Google. This could be any data source. This could be Netflix. Netflix launched in Sweden in October, and me as an exchange point thinks that's a brilliant thing. You should all get Netflix. It's really good for peering. I haven't watched a single film, but clearly everybody else has. But it tells you that these data sources are becoming quite high. There's quite a lot of traffic. And if I were a provider, I wouldn't like to have this 250 gigabit of second on a single interconnect. I probably want to have multiple interconnects. And again, this probably doesn't take into account everything I see in a Google cache and everything I see in other services to this single one provider. And this is not even a high computational data or high volume data as you guys deal with. Oh, sorry, that was actually the 2011 data, and that's the 2012 data. So it's actually even more. I was going to take the other slide up. Anyway, so this is the 2012 data, which is then a little bit more. But, so if you ask this, you can say, is this actually a problem, all this volume? And you have people say, no, don't worry. We got 100 gigabit coming, and it's going to be dirt cheap within a few months. That's the vendors. Or you have people saying, oh, we peer at so many points with Google, it doesn't really matter to us. Or we have so much transit, those are the people with money. Then there's people who think this will be a problem, because 100 gigabit is too much shared faith. I don't want to send all my traffic to Google on a single port or a few single ports, and especially not at their price right now. The other problem, and I think this is more interesting, is the backhaul cost of backhauling this 200, 500 gigabit, whatever it is, of Google traffic or Netflix movies. It's actually quite high inside my network, and when the incumbents come and cry on your shoulder that it's so expensive, it probably is quite expensive to backhaul throughout an entire country infrastructure. Sweden is from north to south is, I think, around 30 milliseconds, and that could be quite a bit of traffic by the time you're done with it. So there are a number of issues with this. Can we do this in another way? And I think we can. So we'll take yet another random country. And the interesting with this country is that when we start the company I work for, who runs the exchanges in Sweden, when we started in '97, we actually started with building exchanges in 4 different cities originally. Sorry, well, these ones here in the south. Luleå up in the north was added much later. So most of the Swedish population is below a line to the south of this, so Stockholm, Gothenburg, and everything. Here is all where all the traffic is. Up here is basically reindeers. And reindeers are cute, but they don't surf that much. But we still believe that it was an idea to have all these cities spread out to the country, because that will give us resilience, and it would actually give you a way to not focus all traffic to Stockholm, and in case there was an issue, we could actually have this distributed. Now, Sweden is not unique in this way. Italy has also done this for a long time. It's starting to happen in the UK, it's starting to happen in Germany. And again, these are public interconnect points. We still have a lot of very dense private interconnects as a complement in these places. The interesting thing, though, is that if I look at Sweden, this is the traffic statistics yesterday for each of the cities. Stockholm is much larger than all the other cities. So this entire idea that we originally would distribute this traffic load around the country, in a way, has failed, because we haven't. It's all there. And part of this is because when the idea came up in '96, '97, and this was built, all this traffic were actually sent between the operators. They were the data source. That's where all the content was, or in the US even. However, today that's not the case anymore, and it's basically only eyeballs that are peering outside Stockholm. So that traffic you're seeing there is mostly peer-to-peer. I don't know, but I assume it's peer-to-peer file sharing. And all the content, all the interesting Netflix, Google, etc., Akamai, Limelight, is all in Stockholm. So all the eyeball networks are backhauling all this capacity into Stockholm. And I believe them. I think that's expensive. I think there are other ways to do this. And again, don't get so focused on this being public networks. This could be any data. having this data pushed out to the edge and having much more CDNs pair locally will bring the cost down. And we are seeing interest by the CDNs to build out to the other exchanges and to push the caches out into the network. And as we're seeing more and more bandwidth consumption, I think that's going to be more and more happening more and more. There is some interesting presentations by Ericsson in Barcelona at the whatever it's called, mobile telephone conference world, whatever, where they're actually bringing the cloud all the way out to the cell tower. Now, if I'm an incumbent or a telco, bringing the cloud out means that I can charge you money. But I think that in the end, these cloud services will be the same services as we have today, because the rights holders, the content owners, are the ones who actually have the content. The rest is just infrastructure or delivery mechanisms. And I think that the CDNs of today are a little bit ahead of the curve, but I think we'll see more and more of this. And I think going out to these regional cities and then pushing this even further out is going to be even more interesting. So that the access, because most of the bandwidth consumed today in the networks is actually on demand. And I'll come back to that. So this is the European network, the European exchange point map from EuroX. These are all the IXs in Europe, and we have quite a few of them. They are small, some of them or most of them, but I think they're growing, and they'll grow in importance to have this content being brought more local to the end users. And again, I think I've gone on enough about why this is so good, but I think that this backhaul cost in the network, to lower it by pushing the actual data out to the edges is the most important thing. There's actually a financial incentive to go and do this, besides the fact that it improves end user experience. And I think that the CDNs in the cell towers or the cloud is just an example of this. And we'll probably see even more of this. And as Steve also said, SDNs and the flexibility that they will allow is actually quite amazing. We have biannual meetings at NetNode with our customers, and the last one we had Bambooser, which you might have heard of, the Swedish company that allows you to do streaming TV from your cell phone. That was very widely used during the Arab Spring to broadcast on Tahrir Square and so on. And they actually used the Amazon Cloud Services for entire infrastructure. And I thought that's quite amazing. They do dynamic allocation of these services as they go along. That tells you how these CDNs have changed how we actually do delivery of content and services. And for them to be able to do this, and for them to have this rapid deployment and easy access to end users, this data has to get closer to the end user to handle the streams we're seeing. This is streaming video, right? And I personally think that's the only way you can make this network scale. And that was me. I guess it's time for some questions then.
So questions for Curtis?
Or comments?
Come on, don't be shy, it can be controversial.
Is the CVI cable still there?
We have, yep.
Hi, Curtis. It's Matt Ford from ISOC. Great talk. I'm mostly familiar with the situation in the UK because that's where I'm from, and I'm sort of vaguely close to the recent developments to establish an exchange point in Edinburgh. I wonder if you think there's a sort of limit to either in terms of the number of, the amount of traffic that's actually being exchanged, the number of people in a particular locality, or a limit to the extent to which this, this road can be followed, because of, I think communities of technologists are also key to making a viable exchange point. So I wonder what your sense of how far this can go is.
If you look at this, and if you look at Sweden, for example, the exchange point up in the far north, Luleå, is very small, as you saw. And there's a reason for that, is that there is no router equipment in Sweden north of Sundsvall, which is the other north point, which means that although people have interconnected there, they're actually sending the traffic via the other exchange point and back up to Luleå, which sort of course kills the idea of having an exchange point there. So I think there are limits to where you can do this, and it depends on how the networks are built, right? But as we are seeing more and more traffic being, take UK for example, where you have the Manchester and Leeds IXs, where the CDNs actually have deployed or will deploy, because they believe that they will save on the backhaul cost from doing it from London. So I don't think there's necessarily a limit in that way. I mean, we're seeing the CDNs deployed in very small places with very little traffic. It all depends on the market share and the benefits of this. We can see the Google cache or the Akamai caches being brought into developing countries. There's enormous savings of cost, not to mention the improvement in end-user experience. In the developed Western world, I think there's also these benefits to be made, just like we've seen in the UK. I think the UK is a great example of where the CDNs actually went and deployed at the small IXs, and this has turned out to be a success for the small ISPs, and it didn't take much of a user base to make that work, right? So I don't think there's necessarily a limit on this, but I do think the topology of the eyeball networks does present a limit to how this can be done.
Another question? John Sylvester from Scenic in California. I found that, thanks very much for your talk and also for Steve's, but I saw these two talks as quite contrasting in their view of what the future holds. In many respects, you're sort of saying, I think, that organic growth of networks and interconnects is sort of the right way to go through peering. And Steve was saying it's sort of time for a more rational international interconnect in the R&E world. How do you sort of bring those two visions of the future together, and which one do we think is more likely to happen?
But I don't think that they are contradicting each other. I think they're complementing each other. I think we have to do both. I think that, you know, the traffic won't stop flowing internationally, but the growth might slow and become more localized, because a lot of the high volume traffic and also I have to say that I think that the traffic patterns of NRENs might be slightly different than the traffic patterns on the global internet, right? So I think that in that way they're also maybe a little bit different. But the commercial networks, I mean, the traffic growth we are seeing is you know, to a large extent to these local services that are on-demand services. And I think that this increasing capacity and high bandwidth, as we're seeing, 100 gig and 400 gig, etc., we need that as well, and we need to have the long-haul systems to handle this, but that doesn't necessarily exclude us from trying to keep more traffic local, and I think we have to have that for the financial sustainability of the networks. So I don't think they are contradicting in that way, actually. I think that you have to do both of them. And again, as Steve was saying, it's about the processing and computing of data. That's, of course, very different to what you see in a commercial environment, where you don't have the same, you know, what you have to do in a commercial network is pair eyeballs with Netflix, right? That's basically the only thing you have to do. If you manage to do that, you're done. You don't have to distribute computational resources, etc., as Steve was talking about, as you do in an NREN maybe, which is very different.
Another question for Curtis? No?
All right.
Okay, well, I'd like to thank Curtis once more time.
Thank you.
Thank you.